Assalamualaikum, my name is Zubair and right now I am here to prove that 14 divides this entire number. This is a little bit blurry here. Okay, 14 divides this entire number for any number of n. Okay. To prove, we shall use mathematical induction. Now, as I discussed before, mathematical induction involves three steps. First, we have to prove that the result holds for n equals to 1, and then we have to suppose that the result should hold for n equals to k, and the step number 3 is we have to show again that the result should hold for n equals to k plus 1. Okay, so for n equals to 1 we have 14 divides 3 raised to the power 4 plus 2 6 plus 5 2 plus 1 3. And if you use a calculator, this is actually true, like 3 to the power 6, 3 to the power 6 plus 5 to the power 3, that's 854. And if we divide this by 14, we have no remainders. We have 61, a number, no remainders. Therefore the result is true for n equals to 1. Now we suppose that the result holds for n equals to k. Therefore, we have 14 divides, just replace n by k. For 3 raised to the power 4k plus 2 plus 5 raised to the power 2k plus 1. Okay. We suppose that the result will hold for this function. We name this equation as equation number 1. Now, the third step, we have to show that the result holds for n equals k plus 1. So when you put this value over here, we have 14 divides 3 multiplied by 4, k plus 1 plus 2 plus 5 raised to the power 2 multiplied by k plus 1 plus 1. 14 divides 3 to the power 4k plus 4 plus 2 plus 5 to the power 2k plus 2 plus 1. Then 14 divides 3 to the power 4k plus 2 plus 4. We just use commutative property on the powers, the exponential functions. 5 raised to the power 2k plus 1 plus 2. Okay, now why did we do this? To have this function. We know that we have supposed that this holds true. So somehow we will extract this information out of this one. So so basically half of our burden will be easier anyway. And then we have, and then we separate this 3 to the power 4 and 5 to the power 2. 14 divides 3 to the power 4k plus 2 times 3 to the power 4 plus 5 to the power 2k plus 1 times 5 squared. Okay, now we expand it. 3 to the power 4 shouldn't be 3 to the power 4. Okay, it's 3 to the power 4 maybe. Yes. And that we have 81 plus 5 to the power 2k plus 1 times 25. We have 14 divides. Now, if we have a 25 over here and a 25 over here instead of this 81, we can take common. All right, we can take common out of these two terms over here. So what we're going to do is subtract 81 by 25. We subtract 81 by 25. We have 6. 1 carries, okay, goes 7. We have 56. So this gives us 3 to the power 4k plus 2, 56 plus 25. We broke 81 into 56 and 25 because we have to match this number with this. Plus 5 to the power 2k plus 1 multiplied by 25. And then we distribute this. 3 to the power 4k plus 2 times 56 plus 3 to the power 4k plus 2 times 25 plus 5 to the power 2k plus 1 times 25. And we take 25 common out of these. 14 divides 25, we take a common. 3 to the power 4k plus 2 plus 5 to the power 2k plus 1 plus 3 to the power 4k plus 2 times 56. Now we have this number that divides two numbers. Okay, this number divides two numbers. And there was a formula that says, we know that if A divides B and B divides C, then if A divides B and A divides C, one number divides two numbers, then A divides bx plus cy. Okay, and x and y, for all x, y belong to the group of integers. In other words, if we go in the opposite direction, if two integers are multiplied by two other integers and they are added, and those other integers are divisible by a, then a is divisible by all of this. This also means that if 14 divides this and 14 divides this, then 14 must divide all of this. Therefore, 14 divided by 25 bracket 3 power 4k plus 2 plus 5 power 2k plus 1, and 14 must divide 56 multiplied by 3 is to our 4k plus 2. We name this as equation number 2, equation number 3. We named one equation, right? Yes. So, and we have this another property of divisibility. Actually, this is the definition of divisibility that says that if A divides B, then there exists a number C that belongs to the group of integers such that B equals to C times A. Okay, so if this happens, well, I mean, one of the two factors is divisible by B, and the whole number is divisible by B. In other words, if, for example, 56 is divided by 14, we have 56 divided by 14, we have 4 and 0 remainders. That means 14 divides 56. And all of this results in an integer. We can say that that's C. Okay, this could be our B, this could be our A, and this could be our C, right? I mean, K is a random integer, and when integers are being risen by a power of integers, that results in an integer. No fractions, no decimals involved. If k equals to 1, k equals to 2, k equals to 3, k equals to 4, any number without fractions or powers, this can never result in a fraction. And if that happens, and 14 divides 56, and 56 is multiplied by this, then all of this number should be equally divided by 14 without remainder. Now 14 divides 56 3 times 4k plus 2 by simple division. Okay, I mean 56 gives no remainders to 14. That's that. But in the other case, 25 is not divided by 14 without remainder. So this should, right? I mean, for all of this to be divided by 14 without remainders, one of these two terms should be divided by 14. This, as we know, is not divided by 14 without remainder, but this, as you can see in in equation number 1, 3 to the power 4k plus 2 plus 5 to the power 2k plus 1, we suppose that this divides to 14, that this is divided by 14 without remainders. Therefore, this part is true, and if this is multiplied by an integer, then using the definition of divisibility, then equation number 2 should be true. And 14 divides 25, 3 to the power 4k plus 2 plus 2 5 power 2k plus 1. Our assumption from equation 1. And if both the cases are true, therefore 14 divides 56 multiplied by 3 to the power 4k plus 2 plus 25 bracket 3 power 4k plus 2 plus 5 power 2k plus 1. So all of this is proven true. Hence our theorem is proved. Thank you very much.